Soldering is a process in which two or more items are joined together by melting and putting a filler metal into the joint, the filler metal having a lower melting point than the adjoining metal. Soldering differs from welding in that soldering does not involve melting the workpieces. In brazing, the filler metal melts at a high temperature, but the workpiece metal does not melt. In the past, nearly all solders contained lead, but environmental and health concerns have increasingly dictated use of lead-free alloys for electronics and plumbing purposes. Origins. There is evidence that soldering was employed as early as 5,000 years ago in Mesopotamia. Soldering and brazing are thought to have originated very early in the history of metalworking, probably before 4000 BC. Sumerian swords from 3000 BC were assembled using hard soldering. Soldering was historically used to make jewelry items, cooking ware and tools, as well as other uses such as in assembling stained glass. Applications. Soldering is used in plumbing, electronics, and metalwork from flashing to jewelry. Soldering provides reasonably permanent but reversible connections between copper pipes in plumbing systems as well as joints in sheet metal objects, such as food cans, roof flashing, rain gutters and automobile radiators, jewelry components, machine tools and some refrigeration and plumbing components are often assembled and repaired by the high-temperature silver soldering process. Small mechanical parts are often soldered or brazed as well. Soldering is also used to join lead came copper foil in stained glass work. Electronic soldering connects electrical wiring and electronic components to printed circuit boards. Soldering filler materials are available in many different alloys for differing applications. In electronics assembly, the eutectic alloy of 63% tin and 37% lead has been the alloy of choice. Other alloys are used for plumbing, mechanical assembly, and other applications. Some examples of soft solder are tin lead for general purposes, tin zinc for joining aluminium, lead silver for strength at higher than room temperature, cadmium silver for strength at high temperatures, zinc aluminium for aluminium and corrosion resistance, and tin silver and tin bismuth for electronics. A eutectic formulation has advantages when applied to soldering. The liquidus and solidus temperatures are the same, so there is no plastic phase, and it has the lowest possible melting point. Having the lowest possible melting point minimizes heat stress on electronic components during soldering, and having no plastic phase allows for quicker wetting as the solder heats up and quicker setup as the solder cools. A non-eutectic formulation must remain still as the temperature drops through the liquidus and solidus temperatures. Any movement during the plastic phase may result in cracks, resulting in an unreliable joint. Common solder formulations based on tin and lead are listed below. The fraction represent percentage of tin first, then lead, totaling 100%. 63/37 melts at 183 degrees Celsius. 60/40 melts between 183 to 190 degrees Celsius. 50/50 melts between 183 to 215 degrees Celsius. For environmental reasons, lead-free solders are becoming more widely used. They are also suggested anywhere young children may come into contact with, or for outdoor use where rain and other precipitation may wash the lead into the groundwater. Unfortunately, most lead-free solders are not eutectic formulations, melting at around 250 degrees Celsius, making it more difficult to create reliable joints with them. Other common solders include low-temperature formulations, which are often used to join previously soldered assemblies without unsoldering earlier connections, and high-temperature formulations which are used for high-temperature operation or for first assembly of items which must not become unsoldered. During subsequent operations, alloying silver with other metals changes the melting point, adhesion and wetting characteristics, and tensile strength. Of all the brazing alloys, silver solders have the greatest strength and the broadest applications. Specialty alloys are available with properties such as higher strength, the ability to solder aluminum, better electrical conductivity, and higher corrosion resistance. Flux. The purpose of flux is to facilitate the soldering process. One of the obstacles to a successful solder joint is an impurity at the site of the joint, for example, dirt, oil, or oxidation. The impurities can be removed by mechanical cleaning or by chemical means, but the elevated temperatures required to melt the filler metal encourages the workpiece to reoxidize. This effect is accelerated as the soldering temperatures increase and can completely prevent the solder from joining to the workpiece. One of the earliest forms of flux was charcoal, which acts as a reducing agent and helps prevent oxidation during the soldering process. Some fluxes go beyond the simple prevention of oxidation and also provide some form of chemical cleaning. For many years, the most common type of flux used in electronics was rosin-based, using the rosin from selected pine trees. It was ideal in that it was non-corrosive and non-conductive at normal temperatures but became mildly reactive at the elevated soldering temperatures. Plumbing and automotive applications, among others, typically use an acid-based flux which provides cleaning of the joint. These fluxes cannot be used in electronics because they are conductive and because they will eventually dissolve the small diameter wires. Many fluxes also act as a wetting agent in the soldering process, reducing the surface tension of the molten solder and causing it to flow and wet the workpieces more easily. Fluxes for soft solder are currently available in three basic formulations. Water-soluble fluxes, higher activity fluxes designed to be removed with water after soldering. No-clean fluxes, mild enough to not require removal due to the non-conductive and non-corrosive residue. These fluxes are called no-clean because the residue left after the solder operation is non-conductive and won't cause electrical shorts. Nevertheless, they leave a plainly visible white residue that resembles diluted bird droppings. No clean flux residue is acceptable on all three classes of PCBs as defined by IPC 610, provided it does not inhibit visual inspection, access to test points, or have a wet, tacky or excessive residue that may spread onto other areas. Connector mating surfaces must also be free of flux residue. Fingerprints in no clean residue is a Class 3 defect. Traditional rosin fluxes, available in non-activated, mildly activated and activated formulations. RA and RMA fluxes contain rosin combined with an activating agent, typically an acid, which increases the wettability of metals to which it is applied by removing existing oxides. The residue resulting from the use of RA flux is corrosive and must be cleaned. RMA flux is formulated to result in a residue which is not significantly corrosive, with cleaning being preferred but optional. Flux performance needs to be carefully evaluated. A very mild, no-clean flux might be perfectly acceptable for production equipment, but not give adequate performance for a poorly controlled hand soldering operation.